עושים עכשיו מטריצה, שפה יהיה לי כל הריאליזיישן של y הראשון נניח, אוקיי? פה יש לי 0.1 שנייה וכולי עד 10 שניות. איך זה וקטור של 1000. כן, זה 10 שניות. ואז יש לי y2 וכולי. עכשיו המטרה שלי זה למצוא את y c דלטה. עכשיו אני יכול לבוא, אני יכול למצוא correlation function עבור זה, כן, נצליח נקודה הזאת ונקודה הזאת וכולי וכולי, אוקיי? אז ואז אני מקבל בעצם עוד פעם מטריצה שפה יש לי את ה-y.
כל שורה זה ריאליזציה? או כל עמודה זה ריאליזציה?
זה מה שאמרתי, נכון? ויש לנו, זה לא משנה, אבל בכל זאת, אז זה CY1, זה CY2, ומה נעשה עליו?
Hi everybody. Can you hear me on the microphone? Yeah, good. Today I'm going to show you an applied model of a dynamical system. It's a one-dimensional model, and I especially like this model in this lesson because it shows you how even in a one-dimensional system, once you have parameters, you can get really different behaviors of the system. And the parameters can drastically alter what happens, and in the natural world, this has consequences. So I really like to have an applied model. So you can think of what this all means. What does the bifurcation mean? And what do the fixed points mean? It's called the in-fixed outbreak model. And through it, we will demonstrate concepts that we went over in the past few weeks, like fixed points, bifurcations, and bifurcation diagrams. And we'll introduce some new concepts, including, and we will also do the dimensional analysis, non-dimensionalization, and scaling that we showed last time, although we will do it in a slightly different way. And we will introduce new concepts, including the stability diagram, and the cusp point, and cusp catastrophe. I also especially like this demonstration because it's completely analogous to what we see in neural networks. So the bifurcations and the stability properties that we will see here also occur in equations that describe neural networks. So it's very useful to see this for students of the ICNC program. Okay, so this model concerns a type of worm. It's called the spruce budworm, and it infects forests in eastern Canada. And the importance of this is that if the population of the worm, of the budworm, grows too much to what we call an outbreak, then it can just eat all the leaves of the fir trees in a certain forest, and then it will take many, many years, tens of decades even, to recover the foliage of the forest. So it was very interesting for ecologists to know what governs these outbreaks and how they can be avoided. So yeah, I wrote here that the worm population can defoliate an entire forest in 4 years, and then it will take about 10 years to recover. But it's more complicated than that. I'll say something about it in the end. So the model for this forest and worm populations was proposed and published by Ludwig in 1978. And the assumption of the model is that the population of the worms grows or reduces at a rate that is much higher than the rate at which the population of the trees can grow and recover. So it's a kind of separation of time scales that leaves us with one dimension that's interesting for us. That's the population of the worms. So the equation is based on the logistic equation that we know already, where this K is the carrying capacity that depends on the amount of foliage in the forest. So you can measure it per acre of forest or something like that. And in fact, it's a slowly drifting parameter. If we would like to model the whole forest, including the tree population, then we would have K as a parameter that changes very slowly. For now, we consider it as a constant. Foliage. How many leaves do you have? And okay, but the population doesn't only grow and depend on the carrying capacity. We also have a term that we mark by P. This is predation. So the worms are being eaten by other animals, for example, birds. And this causes a reduction in the population. It's a kind of negative feedback. And the predation depends on how many worms there are. So it is assumed that it is a kind of a sigmoidal function of the worm population, where as long as the worm population is smaller than some amount, I won't mark it here, I'm not sure that it should be A, So, not really, because if there is a small number of worms, then the birds. So, so yeah. So if there are not many worms, then we say that the birds go elsewhere to seek for food. So you see, there is not a lot of predation. And if there are many worms, then the birds come, and at this plateau, birds eat as much as they can. Okay, so even if there are many, many worms, then there can be a limited rate at which the birds eat them. So we have a sigmoid. And the equation that was given for this was of this type: bn squared over a squared plus n squared. So when n is very large, then the rate of predation is approximately b. It tends towards b. And the onset depends on this parameter a. It's a kind of critical population for the onset of the predation, a kind of threshold.
How did you decide about this term to express predation?
This one? Just because it's an equation that would give this. I guess they just came up with a model. I don't know if they had data, but you would, I don't know, maybe you would see some data and try to find a simple function that can describe it, or just, propose something and then see how it works. Okay, so we have this model. I would like to write it again in the full form: n equals r over n equals rn times 1 minus n over k minus bn squared over a squared plus n squared. And we would like to know under what conditions do we have an outbreak of the population. So intuitively, an outbreak would occur when the population of the worms changes from a low value to a high value, but it's not really clear how to define these high and low values or ranges. So for this, it's useful to do non-dimensionalization. And then we will be talking about a non-dimensional population. So the population is already counted in terms that are relevant for the system. So for example, we could think of two candidates for a non-dimensional population: x equals n over k, and then we would only be interested in how much or by how many times is the population larger than the carrying capacity. So then you would talk about whether it's bigger than 1, smaller than 1, and these might be your high and low populations that define the outbreak. And you can think of another candidate. You see A here should have the same dimensions as the population. It should be also in the dimension of number of bloodworms. So this is another candidate, n over a. So that would mean that we are counting the population in terms of the threshold for onset of predation. Did it pass it or did it not pass it?
So candidates for what? Sorry, I think I missed it.
For a non-dimensional population.
Non-dimensional?
Population.
But both can
Both can work, yeah.
What do you mean by non-dimensional population?
You would like to treat the population in terms that are relevant for the system. So you would choose a scale for looking at the population, and this scale is relevant for the system. So let's say that the environment can support 1 million worms. So let's start counting the worms in units of millions. Okay?
So it's like an indicator to when your outbreak is
Yes. So this would be a more simple way to look at the outbreak, to ask whether the population is larger than the carrying capacity or smaller, or some. Hopefully there will be ranges that are better defined in X than in M.
look at it like that because when your population is increasing over the carrying capacity,
Yeah.
your size is X in K.
Yes.
So
Yeah. Okay. So.
so in this point, an outbreak will not be possible.
Yeah. Yeah. Probably.
So why is it useful to look at the
To look at the non-dimensional. Well, for one thing, you would like to move to. You would like your final conditions. We won't reach these final conditions exactly, but you would like your final conditions to be things like this, okay? Or yeah, and this would translate to n larger by a lot than k, or maybe you would put in here in the conditions some forms of b and a and r, but you would like to make things as simple as possible. So it's possible, you will see that we don't actually care about B, okay? About the maximum rate of predation. It's possible that we only care about this rate in relation to R and to a function of A and K. We'll see this, okay? So like Chagai said, both of these are possible. The question is what is more comfortable for us and more useful, okay? A is a kind of threshold for the predation. Okay, so like I said in the previous lecture, there might be several ways to do the non-dimensionalization. We might try to do it with this x or with this x. And in this case,
How much your goal is? I mean, how
y-
you want
yeah,
the dimensional equation to be? Can you go backwards and then do the steps backwards and see what x you get?
yeah, it's something like that. So
Didn't work out.
what?
Okay.
No, this is exactly what I'm going to do.
Yeah.
Okay. So here we would like to. The tactic would be to simplify the more complex term in the equation, and then push everything else into the simple term. So we would like. We don't know yet if we can do this, but we would like this term to be of a form as simple as possible, including no parameters, no new parameters. So we would try to transform the variable n and the parameters a and b in a way that we will get to this expression in the second term, and everything that will come out, everything that we will need to take out of the expression will go into the first term and the left side of the equation.
Does it matter if it's 1 or any other constant?
It doesn't really matter. Just convenient to have 1.
What is the motivation to do it? I mean, why do you want extra over 1?
Because if there would be any parameter remaining here, like b, or like Chagai offered b here, then it will be harder to know what the effect of the parameter is on the equation and on the fixed points. So I don't want parameters interfering with this function that for me is a little complex.
You choose that term because this is the more complicated?
Yes. So anything I do here will not change the fact that this term is a parabola and this term is a sigmoid. So, and it's easier to know what happens to a parabola. It can be shifted up or down or sideways. So I'd like my parameters to go into the the parabola and leave this free of parameters. You'll see it will become clear, I think, when we plot them one next to the other. Okay. So we'd like to transform this into this. So the first thing we can do is take the a out of the denominator. So and then I just put it into the numerator. This is great, right? So I already know that my chosen candidate for a non-dimensional population will be n over a. So I'd like to rewrite the original equation using x. Okay, so n equals ax. I can substitute ax for n everywhere, and dn equals a times dx. So I'll write the equation again. I have a dx over dt equals r a x times 1 minus ax over k. And then I subtract the predation term. So minus b x squared over 1 plus x squared. This is already pretty good. No.
Didn't you say that you want to create a situation in which all the parameters will be in the
Either here or here.
but didn't you say you also
I have b, so I'm going to get rid of b.
no but also inside X you have A. So like cheating.
Inside x I have a, right?
And
Yeah, no, this is okay.
right? You said that the motivation is
Oh, no, so all the remaining parameters, all the new parameters that will remain after choosing a non-dimensional variable and trying to group the original parameters into non-dimensional groups. So you would try to find combinations of the original parameters that give you a dimensionless quantity. For example, instead of having k, instead of having r, which is a rate parameter, you would like to have non-dimensional parameters. So you would multiply r by a time scale. And you would remain with capital R, maybe? Or maybe, how did I write the model? Oh, okay. So you would remain with a capital R, a new parameter that has no dimensions. So all parameters of this type you want to have here, or put them here and then push them into the new time variable. So, okay, 1 over b dx over dt equals RA over dx. Okay. Of course not. So we already got our desired form of the second term. And now we would like to try and simplify things here as much as we can. So first of all, we don't want to have these things here in the end. And if I start multiplying or dividing, I will mess up my simplified form here. So I will choose a new time scale, a new time variable. So I would like to have a d tau that will be equal to dt times b over a. And this means that tau should be defined as b over a times t. Dt times b over a. So there will be a division by d tau here. So I define this, and now I have dx over d tau equals r times a over b, 1 minus ax over k minus x squared over 1 plus x squared. So we shifted to a new time scale. What we should do at this point, or before substituting even, is check that tau is dimensionless. Not in every model you would reach dimensionless variables, but you should try to get it if you can. So we do now, actually we backtrack and do something we should have done in the beginning, which is to do a dimensional analysis and see what are the dimensions of each of these. So the dimension of n, last time we used kilo people, and now we will have kilo worms. And the dimension of a is also equal to kilo worms, and the units of a, basically. Also the units of k, the carrying capacity, and the units of b. B has, excuse me? Over time. Yeah, but not worms. You already have here worm squared over worm squared. Yeah, worms over time. Sorry. You're right. I got confused. So worms over time, say per day, and R just 1 over day. Yeah, sorry. So we can do the analysis for tau. Units of tau equals the units of B, that's worms per day, divided by the units of A, that's worms, times the units of the time, which is day. So everything cancels out, and tau is indeed a non-dimensional variable. Okay, and now it's just simplifying things. So I will define, this was capital K before. I will define K over A as a new variable lowercase k, and I will define a new variable. Let's call it s. It was supposed to be lowercase r, but then I accidentally put the lowercase r in all the equations instead of a capital R. So now we are left with s. So our new form of the equation will be dx over d tau equals s times 1 minus x over k minus x squared over 1 plus x squared. And we should check, well, obviously k over a has no units, and r times a over b also has no units. It's 1 per day times kiloworms divided by kiloworms per day. So it's kiloworms per day divided by kiloworms per day. And s has no dimensions. So this is good, having new parameters that have no dimensions. Now you see how they are all in the first term. There was, I lost in x, right? Sx. So k and s are the only parameters, and what's interesting here is that from an equation with 4 parameters, 1, 2, 3, 4, we reached an equation with only 2 parameters. So if you would try to investigate this model, then you might run simulations with different values of the 4 parameters, and it's a 4-dimensional space that you want to investigate. But the non-dimensionalization that we did tells you that you don't need to check all the combinations. You only care about 2 parameters, 2 new parameters that are actually ratios between the old parameters. Okay? So I don't care how the model behaves for each possible carrying capacity, for each possible onset of predation. I only care how it behaves for different ratios between the carrying capacity and the onset of predation. And this greatly simplifies my investigation.
What's the disadvantage of this now?
Are you asking, is there a disadvantage?
Yes, there is some, right?
There is some disadvantage. One thing is that it might become less intuitive to deal with these parameters. And another is that sometimes when you derive analytically, say, the fixed points and their stability properties, you would get expressions, say an expression that says, if this is bigger than that, then the fixed point is stable. And these expressions may be very complex, and one way to check that your derivation was correct is to analyze the dimensions of everything, the numerator and the denominator, and see that all the dimensions cancel out. When you do all the analytical derivation on non-dimensional parameters and variables, you have no way of checking yourself. Okay, so we reached this non-dimensionalized form. Sometimes you see in articles very complicated derivations that are really hard to follow, and defining new variables and redefining until they reach something that is non-dimensional. So this is relatively simple, and we got really a non-dimensional form. So now we have a simplified system. We'd like to find, first of all, its fixed points. I'll just do it here. So fixed points, we'd like to demand that dx over d tau, because x dot is by definition dx over dt. So I must write dx over d tau equals 0. And we have one fixed point always at x equals 0. And once we eliminate that, we can divide by 0 and have 0 equals s times 1 minus x over k minus x squared over 1 plus x squared. X. So I divided by 0, and now I would move this to the other side. X over 1 plus x squared equals s times 1 minus x over k. You could continue solving this. It means you would get cubic terms, and you would have to use the cubic equation, which is not very simple. But you can solve it analytically. But what we'll do is, as always, we will use the geometric method. That was. So we draw these two functions. I will give them names, okay? So this will be G, and this will be capital P, because I already used the lowercase p. So G is just a line, right? So it's when x equals 0, G equals S. And when G equals 0, x equals k. So it's a line going from S to k. Okay. These ranges don't interest us because x is a population. It can't be negative. Okay, maybe it's, and this might interest us, this range. So x over 1 plus x squared. To draw this, you will check what happens when x is very small and when x is very big. When x is very small, you can neglect it. So this function near 0, it goes similar to y equals x. And when x is very big, then you can neglect the 1, and you're left with 1 over x, which looks something like this. And you have a connection between them. So this is the way this function looks.
What's the y-axis?
The y-axis is, I'm just plotting two functions versus x. So I don't have a name for the y-axis. This is P, and this is G. And I would like to extend the scale.
So
Yeah?
how do we know that it doesn't do it beneath the graph of G?
Oh, we don't know.
We don't know.
We don't know. This is my next point, that depending on S and K, there can be different intersections between these two curves, and of course the intersections are our fixed points, right? So S, it's R. No. I should have defined it in the first place, that R is positive and A is positive and B is positive. Okay, so we could imagine, and we could even draw several situations. So, of course, if K is big, then we might have two intersections, actually three intersections, right? If S is big, yeah, and if K is big but S is also big, we might have one intersection again. We'll draw this systematically and you'll see how we deal with this. But this shows you one of the advantages of having only two parameters instead of four of the process that we did. So now we have only two parameters to play with. They shift the slope and the intersection of the line with the y-axis. And this form, this x over 1 plus x squared, this stays the same for all the parameters. So I don't need to start thinking how changing a parameter changes this curve. There is no parameter in this curve. Everything is controlling the line, and it's really a lot easier to look at the line in relation to this curve, to this non-monotonous curve. Okay. So let's take a break now. Is that okay? And come back in 10 minutes. זה חלק מהמטרה שלנו, ש-X יהיה פרמטר שהוא מקביל לאוכלוסייה, אבל כשאנחנו אומרים ש-X שווה 2 שווה 10, יש לזה יותר משמעות מאשר להגיד שהאוכלוסייה היא 1,000,000 או 2,000,000 בגלל ש-X הוא כבר כולל בתוכו את הגדלים שרלוונטיים לאוכלוסייה.
לא, אני רוצה, למה הוא לא עשה את זה גם כחול ואדום?
הוא לא יכול לתת לי להגיד מדע ל-Outbreak, כי אם הוא יהיה גדול מאחד, אז אני יודע שאני אוכל לבדוק. לא, אוקיי, אני לא חשבתי על זה בזמן השיעור, אבל יש עוד נקודה אם לא... אוקיי. קודם כל יש שני כוחות שפועלים על האוכלוסייה. אחד זה קשור ב-carrying capacity, זה קשור לגידול. אז נכון, אז אם האוכלוסייה עברה ל-carrying capacity, הכוח הזה ימשוך אותה למקום. הכוח הזה, הכוח הזה ימשוך אותה לקטון, אתה לא יודע איך הוא פועל. אתה לא יודע כשהיא תעבור את K, הכוח הזה כבר פועל, או שהוא עוד לא פועל. שעברת את הקרן כפסטי, יש איזשהו מדד ל-Outbreak. אבל חשבנו קודם שכאילו זה חלק שכולם רוצים הרי הכל משל שניים. לא הגענו די לדבר על זה. שתי יחידות שבורות, זה נראה לי נורא דבילי. הוריד לכולם את זה. לא, צריך להגיד לו, הוא הוריד למישהו על טעות.
הבסיסי הראשון עד ל10 שניות, אוקיי?
אוקיי, כל המודרליזציה.
כן, ריאליזציה אחת, בדיוק y1 וזה y2. אוקיי, ועכשיו יש לי הרבה כאלה. עכשיו כשאני אעשה את זה לפה, כשאני אעשה פה
עבור דלתה ספציפית, כן.
עבור דלתה ספציפית, אז אני מקבל אותו y, c, y1,
אני לא יכול לעשות את זה. אני לא יודע כלום על הנקודות שבט.
כי זה קורלציה
אני לא יודע איך הם לראות.
אני לא יכול לעשות של...
ברור, אבל מה שאני עושה זה...
איך אני יכול...
יש לך כאן הרבה דוגמאות. נגיד אתה עושה עם... זה צעדים, כן. אז אם אני עושה, נגיד, עבור דלתה שזה טיים סטפ אחד, אז אני עושה, נגיד שזה ה-T הראשון שאני מתחשבת בו, אז אני עושה את זה, לזה, לזה, על כולם.
את מקבלת את זה, y1.
אני עושה את זה על כל אחד, אני עושה ממוצע על כל אלה, ועל כל אחד מהם אני עושה ממוצע.
אתה צריך להסתיים עם הנושא
בהתחלה על וקטור, ובהתחלה
אני עושה במקביל על כל הוקטורים, אבל על כל אחד בנפרד.
אם יש לנו את הדבר הזה, מחליט עכשיו. מה הדבר הבא שאת מקבלת?
אני לוקחת פה, אני עושה את הממוצע על כל הדברות, אני מקבלת ממוצע. כאילו מספר אחד של הממוצע. אותו דבר אני עושה לשני, אותו דבר לשלישי, אז לכל אחד אני מקבלת מספר,
אז אני יכול להגיד ש...
ואחרי זה בעצם מה שאני ציירתי פה, CY1, CY2, ואז הדבר הבא שלנו, כאילו יש 3 שלבים, 1, 2, והשלב השלישי זה שבעצם כבר עושה מין בין זה לזה, בין זה לזה, בין כל אלה. אני לא יודע אם זה נכון, אבל...
אמרתי לו שאני עושה ככה והוא אמר שזה בסדר. אם הוא מבין מה שאלת, אני עשיתי מה שאלתי, אבל לא ראיתי את הגרף שלך, אבל הסתכלתי על הגרף של מיטל, והרבה דברים סתם שלי.
אז אני יכול להגיד שיש לי פה איזשהו A.
כמה ריאליזיישן?
גם תלוי איזה דלתה את עושה.
אני לא יודע עכשיו איזה קו לצייר עכשיו.
איזה דלתה, אבל אם את רוצה להגיד... לא, לא... מה הגודל של הדלתות שאת מסתכלת עליו בכלל? מ-1 עד 9? יכול להיות שזה משפיע, כאילו מ-1 עד 9.
כל קו מייצג נקודה.
אבל אני לא יודע, אולי זה הקו הזה.
לא יודעת, יצא, אני חושבת שדומה למיכל, אני לא חושבת.
אני לא יודע, אתה מבין, אני יכול להמציא לי גם קווים, אולי זה הקו הזה. אולי זה הגרף הזה, אני לא יודע.
בסטוכסטית נכון את ה...
לא, אבל זה נשמע לי
אתה לא צריך להיות מאוד מדויק, אתה צריך להראות קווים שנפגשים.
לא יודעת, מה שעשיתי זה
לא קשור למדויק, כל מה שאני יודע זה שגם שמאל וגם ימין יהיה לי קו אחד אנסטייבל וקו אחד סטייבל, אני יודע מה יהיה לי ופה אני יודע שיהיה לי אפס, פה לא אספות את זה לא. אני יודע שפה יש איזשהם שני קווים, אחד מקווקו ואחד לא, וגם פה, אני לא יודע איך אני נראה.
נראה לי, לא, אתם אמרו את זה
א' אתה יכול לחלק, ב' אתה יכול לחלק את R למספר, כמו שעשינו שבוע שעבר, לאיזשהו פרמטר,
אז דבר אחד, בהתחלה כשאת מחשבת את הממוצע של YT על YT ועוד דלתה, את מגיעה לביטוי עם שני רכיבים, שאחד מהם של איזה יתר,
כשאני עושה את הממוצע של
YT כפול YT ועוד דלתה, את מגיעה לביטוי
לא,
שיש
זה
שני
כאילו
רכיבים.
קומוניקציה,
אחד
אני לא יודע
מהם,
מה
את
לעשות.
יכולה כאילו... כן, אחד תלוי בדלתה, אחד תלוי ב-T, ואת כאילו ביטלת אותו. שאלה למה את יכולה לבטל אותו
זה מה שדיברת על אתמול,
אני לא יודעת שאלה.
למה, כשאת אחר כך מציבה את זה, באינטגרל שאת מחשבת את זה, יש בפנים את הדבר, זה מתבטל, אני שאלתי אותו והוא יתבטל בסוף בכל אופן, אבל הוא לא חייב
אני אגיד לך
להתבטל.
למה, אני אגיד לך שאני יכול לעשות את זה, בואי תרשום את השאלה.
אוקיי.
למה בווריאנס אנחנו לא הולכים ש-T הולך לאינסוף?
לא,
בקורלציה?
אני מניחה שהולכים לזה ש-T הולך לאינסוף, סבבה? כל האינטגרל בסופו של דבר הולך לאינסוף, אבל את מציבה רק חלק את מתוכו ויש לך אחר כך כפול, ביטוי שהולך לאפס, אז למה את יכולה להגיד?
אני לא מבינה, אולי...
אני אראה לך אולי מה...
העניין הוא שבדוגמה שהראית, ב-F ל-DX הראשון, אתה מציב את זה עכשיו, זה אמור להיות אפס, אבל פה זה לא יצא לי אפס. אז לא יודע אם טעיתי או שמה...
אם זה סטארדון נוד באפליקיישן, זה צריך אפס. עכשיו גזרת לפי X, יוצא לך שני סינקים.
ואז אתה רוצה להשאיר וחצי את ה-R, שאחד מהם זה 2. אתם טעיתי
אבל ה-R פה לא נמצא בביטוי. ה-R נפל בזה.
למה? x 2x חילקתי, זה האינטגרל של זה, לפי מה שאני מבין. חלקתי לאן, נכון? או
אני
שטעיתי
לא
פה
זוכר
באינטגרל?
בדיוק, אני מפרק את זה לשני מחוברים ש... כן, לאן x
מינוס לאן x מינוס 2, יכול להיות? עכשיו ברגע שאתה מביא 2 לפה, יש לך שתי c, כשאתה מוציא את ה-e, אז גם ה-c הוא נמצא למעלה, נכון?
אבל c, כשיש חיבור במעריך, אז אפשר בעצם כפל של... אפשר לעשות את זה לכפל כלשהו.
כאילו, אם בשתי c ואז להפוך...
לקרוא לו בשם אחר.
ואז לקרוא לו c.
לא, אוקיי, אתה צודק. אז
רגע, אוקיי, אז
אוקיי, לא, אבל רק שזה ישאר בעצם, כאילו,
ניסיתי למצוא את c אוקיי, לא, נראה לי זה עליתי על זה, אוקיי, תודה רבה.
אני לא בטוח, אנחנו יכולים לעשות את זה רק אם...
את לא צריכה, כאילו בסדר, מה שהגעת אליו זה בסדר, פשוט לפי מה שאני הבנתי ממה שדיברנו על זה אתמול, אז ההגדרה של הקוונט זה יהיה הגדול שהגעת אליו, ואת צריכה לוודא שבאינסוף זה מתכנס. בטוח שזה בדרך. אבל בעיקרון, כאילו, די שכנעת אותי שאין הצדקה להשיג מראש.
תשכנעי אותי שיש, לא יודע אפשר
we saw how changing the two parameters would shift the line with respect to this curve. And I would like to consider more specific cases, do this more systematically. So first of all, let's consider the case where k is small. Small k. Then if I plot the two functions versus k, versus x, sorry. So if k is small, say k is here, then it doesn't really matter what r is. R can be any of these values, s. I will only have one fixed point in addition to the fixed point at x equals 0. And the situation, the phase portrait would look like this. So I have a fixed point at x equals 0, and I have a fixed point here somewhere. And the original equation, actually the non-dimensionalized equation, has the growth term, that's the linear term, what became the linear term, minus the predation. So in a small range near x equals 0, this is positive, but then the predation term becomes larger, and it will be something like this. So this is a stable fixed point. Now I'll consider the case of large k. And this is basically the way that you should deal with any system that you get like this. Start looking at ranges of the parameters that you have. Choose a parameter and ask what happens when it's small, what happens when it's large. Does this depend on the other parameter? So here we chose k. When it's small, it doesn't depend on the other parameter. And when it's large, we now will have to consider different values or ranges of s, the other parameter. Yeah.
What is the arrow of s?
So these lines are for increasing values of s. Yeah?
Does it matter that if 0 is half fixed or half stable system? So we don't have the negative.
We don't know, so it doesn't matter.
Okay.
It doesn't matter. So if you consider a mathematical system, you'd like to see all the range. But since this is a physical system and you have some physical limitations, then you treat this as some border that you can't pass, and you don't care what happens below it. If you run a simulation, sometimes you will put in a condition that does not allow you to get to negative values. So sometimes it will become a stable fixed point even though it doesn't have to be because of the physical limitation. Okay, so now for the large k case, this is x. I need to draw it like this. So let's say k is here. Now we can consider different ranges of s. So first, let's consider a small value of s. yeah, I call it alpha. So here there is, like we had before, one fixed point in addition to the fixed point at 0. So I can draw the phase portrait. And it's similar to what we had before.
Isn't the dx over tau? Is it tau?
Yes.
You can say it exactly like CK small k over the maximum point of B, right? If you take k over the point of B, my k will be my S is more than 1. If you take,
If I take k that is larger than this value,
yeah,
not yet.
no? Why
No.
not?
From here, you mean that from here I might get two intersections? So no, I need the line to. The limiting case is when the line is tangent to this point here. You'll see how we get it. We get these things numerically or indirectly later. Okay, so this was for s equals alpha. And I call this first fixed point other than 0, I call it A. I would like to give names to the classes of the fixed points that I get. The next, okay, like I just told Chagai, the next case that's interesting is this case. I'll call it beta. S equals beta. X, okay. Just assume that this applies to all the axes. S equals beta. So now the fixed point that I previously called A is at a higher value, and there is another fixed point here. If I draw the curve, it will be tangent to the x-axis here. So this is an half-stable fixed point. Which I will call B. Well, I won't call it yet. Yeah, right, of course. I want you to note how neighboring fixed points must have opposite stability properties. So here we have an unstable and a stable fixed point. Unstable, stable, and a half-stable, but it turns its half-stable side to our stable fixed point. So this is a kind of limiting case, and the next case is actually a range. I'll call it gamma. And here I have three intersections. X. So A is shifted a little more, and these intersections have actually come from this half-stable fixed point. It's kind of divided into two fixed points, and the stabilities, like I said, are alternating. Okay. The next case I want to consider is another borderline case where the line will be tangent to the curve. I'll call it delta. Now, I'm left again with two intersections. And so this intersection is the result actually of the merging of two fixed points. This was A, B, and C, so A and B merge. And C still exists, it's shifted to a higher x. And the x, the time derivative should look like this. No, again, I made a mistake. Say again? This was A, so A existed until it merged with another one. This was the beginning of B and C, so this was B, and then it merged with A, and this was C. It's starting to increase its x values. I imagine this line. I imagine it moving, and I look at what happens to the intersections. So these intersections will merge into one and then disappear. Okay, the last case we will consider is when S is very large. Call it epsilon. We'll have only one fixed point other than 0. Okay, so this is something that it's very useful to do. It's a lot of work, but it's useful and gives you a good picture of what's happening here as the parameters are shifted. And it also gives you the stability properties. It's a good way to derive the stability properties. Okay, so we'd like to understand this better and see what's happening here. I would have made the plot here, but I don't have any space left. So I'm going to do the bifurcation diagram for these cases. So this will be versus x versus s for large K. Okay, so we always have an unstable fixed point at 0. I can already draw this. And then we have the fixed point at A, that stable fixed point. It's increasing and increasing and increasing until it merges with B. So this will be its curve. At a certain point beyond S equals delta, the fixed point A stops to exist. Now,
how do you know how to draw this blue line?
I don't exactly know. I'll say something in a moment about what I do know. Now, the fixed points B and C were formed at a certain value of S, that's the value beta. So they were formed somewhere above A. B is unstable, and once formed, as I increase S, it starts moving towards A. So this is this branch here, and C is stable. And it will just move, increase in X indefinitely. So regarding your question, what I do know is that bifurcation like this is of course a saddle node bifurcation. It looks, this is the way it looks. I mean, it does not look like this, okay, or like a corner. It's this is a parabola. It's related to what we, if you remember, when we first learned the saddle node bifurcation, we had these plots of x dot versus x, and our curves were going like this. So from the moment the fixed points are formed, the way that they separate from each other in the saddle node bifurcation is initially according to x goes like a square root of s, like plus minus square root of s. So very near to this point, you have two curves that are approximated by these square root curves. And about this, I don't know. Maybe it's concave up. Okay, I'm not sure about it. Just do it so that it looks nice.
The saddle node is x equals s at the point of where delta?
The saddle node, x equals s? No.
X equals delta, right?
Delta, yeah. There is one at delta and one at beta. So this will be the range that I called alpha. This will be the range that I called gamma. And this will be the range that I called epsilon. What else do I want to say? Oh, I can label the branches. Well, I talked about it already. A, B, and C. Okay, A is called in this model the refuge level, and C is called the outbreak level. You can see that A has low values of S, so small populations. And C has high values of X. So we see here the separation that we were looking for, the definition of what is the low population and what is the high population that will be considered an outbreak. We see that there are two ranges that are they have a separation between them. So there can be low populations and there can be high populations, but there cannot be intermediate populations. Only transiently, but not stable intermediate populations.
Beta is just underneath where
Yes.
underneath the saddle node, right?
Yes. Sure. Gamma is the bistable region. And okay, obviously we would like the forest to be on at this branch, to be on these fixed points A that depend on S, they depend on K, but we wouldn't like to have it at C, and the transition to C can only occur, first of all, if S is larger than beta, and second of all, if our initial condition or our perturbation takes us to an S that is larger than B. So we can be here, the force can be stable here for years maybe, and once there is a perturbation that brings X to a value that's larger than B, the fixed point B that is defined for that value of S and K, then immediately the force will transition to this fixed point where there is an outbreak, and the n6 will devour the foliage of the forest. And you can see that okay, so say S is shifting slowly, right? And the forest is at the refuge level. There is also a possibility that a slow drift in S will make A disappear, and we will be able to be only at the outbreak level, right? If S is increased, we are on A, we're forced to increase the population until there is no stable small population for large values of S, and there is an outbreak. And you can see that there is hysteresis here. So if I draw the curve here again, and this is X versus S, so this slow drift in S that I mentioned can take us to a point where we must go to the outbreak level, and then if S will be changed again, will be decreased, maybe the foresters will manage to intervene and decrease S, it will not help, okay, because decreasing S will keep us on the outbreak level. We'll still be in an outbreak unless we decrease it enough that the outbreak level does not exist and we can go back to the refuge level. This is the hysteresis.
There's a jump.
Yeah. Yeah, there is still.
There's no continuum like population between X and
No. Okay, transiently there is a continuous change, but it will be very fast, and we don't deal with this. We don't model this here. You can do it numerically with simulation, but you care about what happens when the transients subside.
What is the meaning of the word hysteresis?
What?
What is the meaning of the word hysteresis?
It's a path dependence. Okay. It comes from a word meaning lag, or falling behind. Okay, so now this is a bifurcation diagram like we saw before, but the situation is more complex. Obviously, we have two parameters, and we would like to know what happens when we change both these parameters. So we already know that this picture does not exist for any k, and we would like to see the general picture. So I'm going to start with a tentative drawing. Okay, and S, one versus the other. And I'm going to draw here different regions, and I'm going to put in what I already know about these regions. So we already know that for a small k, for small values of k, we have only two fixed points, and one of them is stable. We know that for large values of k, we have three different regions, right? So I don't know the borders between them right now, so I'll just draw this as a rectangle. Here we have two fixed points and one stable. Here we have four fixed points, 1, 2, 3, 4, and two of them are stable. And here we have again two fixed points and one is stable. That's the outbreak. And okay. So if I draw for this region x versus s, I should have something like this. So the fixed point rises, let's say. And I could do this for different regions. If I mark some cross section here, then this is the bifurcation diagram that we did. Yeah. This cross section going that way. And I would like to know everything I can here. I would like to know what exactly is the shape of this region. Okay, so for what values of k and s does the bistable region exist? For what values of k and s is there only one stable point, which is the outbreak? What does this look like? I mean, it appears here that there is a path from the refuge to the outbreak that does not involve the bistable region. You can kind of bypass it maybe. So our next mission will be to try and find the borders of the existence of the bistable region. Okay? We'll need to erase something. Okay, so this is empty also. Right. So one thing I could do is calculate expressions for all the fixed points and see where do I have existence of two fixed points and where do I have existence of four fixed points. So this will involve going back to the original equation, to the equation we derived. Sx times 1 minus x minus x squared over 1 plus x squared, x over k here. Demanding that this will equal 0. And now since I know that x equals 0 is one solution that exists always, I will do this. I take out, I divide by s. And then I can put this here, x 1 over x squared, 1 plus 0 k, s. Then I can maybe multiplied by 1 plus x squared, and then I will get cubic terms. So like I said before, possible to do analytically, but not very convenient, or very inconvenient. So instead of looking for expressions for the fixed points and definitions that will tell us how many fixed points there are in each region, we will look for expressions for the bifurcation points. So bifurcation points, like we learned previously, are places where fixed points might come into existence or disappear. So if there are regions with 2 fixed points and a region with 4 fixed points, they must be bordered by bifurcations. So the bifurcation points that we saw in the bifurcation diagram are in fact curves in the parameter space of S versus K. This is also a definition that you should know. This is a parameter space. And of course, this is not the original parameter space of the system. This is a space of the non-dimensional parameters. Okay, so I'm looking for expressions for the saddle node bifurcations that we had. We had 2 saddle node bifurcations. And you remember maybe that when I am looking for fixed points in general, when I do manipulation on this equation, then it might be easier to solve for S or to solve for K, right? Instead of solving for X. So I will be looking for curves S as a function of X, K as a function of X, that will give me that will define the bifurcation points. And these are called parametric curves. Okay, not related to the fact that these are parameters in our model, but related to the fact that sometimes we have some what's called a parameter. Say you have a particle moving in space in the xy plane maybe, and you want to plot its trajectory, and you have x versus t and y versus t, and you would plot x, y later, and for the curve, it will be a trajectory where t is increasing along the trajectory. This is called a parametric curve. So this is what we'll do here. We will use x as an independent variable and look for expressions that give us S and K. And the conditions that should be met in the bifurcation point are, first of all, I'll write it over there. First of all, a bifurcation point is a fixed point. It's a place where fixed points merge. So it should obey the condition dx over d tau equals 0. Second of all,
Right parameters, right? For some parameters to be fixed points.
What?
For some parameters.
Yes, we are looking for the parameters that will give us this. And will also give us another condition. And to illustrate this condition, I want to draw again the 2 components of the equation, one versus the other. So in one of our borderline conditions, remember, we had the 2 curves tangent here. So the tangency is another condition. The condition on the tangency is a condition on the slope, on the derivative with respect to f. So I will write d over dx of, this is not actually p of x, this is p of x over x. If you remember, we divided the original equation by x, and and this is how we eliminated one order from the equation. This is equal to d of dx of g. Okay. I'll write this more explicitly. Our two conditions are now s times 1 minus x over k equals x over 1 plus x squared, and 2 d of dx of s times 1 minus x over k equals d over dx of x over 1 plus x squared. So this is the condition on the tangency. This is p over x. This is a g over x, and that's when it's p over x. Yeah?
And in that condition, you said that the bifurcation point is fixed point, but there's something I don't understand. The bifurcation point is derived from k and s.
The bifurcation point?
It's not a point
Yeah.
of x or something. I don't understand the intuition from
The bifurcation point is, yeah, it's a point on the x-axis or on the k-axis, or in the ks space, right? It's a point on the k-axis. It can be a point on the k-axis, right? Here, where a fixed point or two fixed points merge and vanish. It can be a point on the s-axis when two fixed points merge and vanish. So this point here.
Okay.
On the plane, it might be a curve. This is the bifurcation. It's a curve on the sk plane. But anywhere on this curve, the first condition is satisfied because this is a fixed point. This is a half-stable fixed point, if you remember. So the bifurcation always occurs for a value of x that is a fixed point. At the bifurcation, there is a fixed point, either losing stability, gaining stability, disappearing, appearing, but there is always a fixed point for that value of the parameter, k or f.
So,
Yeah.
could you repeat what are we doing exactly now?
Yeah. Now we are trying to get the exact border of the bistable region.
Okay, and so can you just quickly go
Yeah.
over what we did?
The border of the bistable region is different from the other regions in that it has more fixed points. And fixed points must appear via bifurcation. So the two conditions that the bifurcation, yeah, these are the two conditions that exist in the bifurcation. First of all, there is a fixed point, and second of all,
That both
the two components of the equation are tangents.
okay.
Yeah.
Should it be gx over x or something like that?
Yes. Okay, we don't have much time left, but we're actually at the end. Okay, so now it's basically just solving these conditions. Okay? I'll start from condition 1. I want to do it here. Okay, I'm starting from condition 2. Okay? So I differentiate with respect to x. I get on the left hand side minus s over k. on the right hand side, it's a division of two functions. So it's 1 plus x squared minus x times 2x plus 2x squared. 1 minus x squared over 1 plus x squared squared. So I got this, and then I can go to condition 1. So I open the parentheses and I get s minus s over k times x equals x over 1 plus x squared. This I have here. So s plus 1 minus x squared times x okay. So this is a common factor. So s equals x over 1 plus x squared. There is something wrong here. Oh yeah, I'll make it a common factor. I multiplied this expression by this in order to have this. And then I subtract what I get from the other side. Right, so the 1 and 1 cancel out, and these add up. Um, 2x to the third over 1 plus x squared squared. Yeah. This is already very good. I have s as a function of x. I can make up many values of x and find the values of s where the bifurcation occurs.
Also k you need to find, right?
What?
You need to find the right k.
Yes, and now I want to find the right k. So I have this expression s over k equals this. I'll just give here the result. K equals 2x to the third over x squared minus 1. Okay, so if you remember, k is a positive parameter, and this means that this must be positive, and I have this condition x larger than 1 to have k positive. So I told you I will invent many values of x, then I can start from 1, or actually from 1 and a bit. Okay, so I got my two parametric curves, x as a function of x and k as a function of x. And then I would like to plot s versus k. Right? This was our parameter space, s versus k. So for each value that I can think of x that is larger than 1 is actually a fixed point somewhere on this plane. And not only is it a fixed point, it's a bifurcation point. There is a point in parameter space where this value of x is actually a bifurcation point. And I'd like to see where these bifurcation points are because that would be the border of the bistable region. So we are really near the end, and I want to show you a numerical plot of this. Here, this axis is the abscissa is K. This should be S. And here we have this curve that I plotted for different values of x. So you could imagine x is increasing over these curves, like from here to here maybe, or the other way around.
We see here the S corresponding to the K, and so so for the same K we have two S
Yes.
corresponding to this thing?
I see it on a log scale for K. So here, this is actually the bistable region.